So now that we've calculated all types of limits of sequences, I just want to go back to one of the points having to do with the theorem that we've been using. This is the theorem that basically says we can evaluate the limit of a sequence the same way that we would evaluate the limit as x approaches infinity of any function. I recall that I cautioned you that while it's true that if you just replace the variable n with x, which we haven't even been doing, we've just been using n directly, and you evaluate the limit and you get a limit, then you can conclude that's the limit. But what happens if you don't get a limit? Can you conclude, therefore, that there is no limit? And what I wanted to caution you about is this point, that the theorem does not say that if the limit doesn't exist, then of the function doesn't exist, then the limit of the sequence also doesn't exist. This is an important point because we often think of theorems sort of in this way. We understand, oops, there we go. We understand that a theorem is kind of a statement like this, like if hypothesis, then conclusion, where H is the hypothesis and C is the conclusion. Usually you learn this in geometry class. You say, if it is raining, then the grass is wet. The point is, the converse of the theorem, which would be if C, then H, where we switch the statements, is not necessarily true. And if you think about it in the context of grass is wet and raining, think about this. If it's raining, the grass is going to be wet. But if the grass is wet, that doesn't mean it rained. It might be the case that the sprinklers were on, or someone spilled something on the grass. So it's not the case that the converse of a theorem is automatically true. So here, what we have is a theorem that says that if this is true, if an equals fn and the limit of f of x exists and equals L, then the limit of an is also L. It doesn't say that if this is not true, then if it doesn't say that if this is not true, then the limit doesn't exist. So I want to demonstrate to you a situation where that's the case. So consider this. Let's let an be this sequence, cosine of 2 pi n. Let's find the limit of the sequence or show that the limit does not exist. So the sort of naive way to do this would be to say, let's let f of x equal cosine of 2 pi x, and then try to calculate the limit as x approaches infinity of cosine 2 pi x. Now we know that cosine of 2 pi x is just kind of a compressed version of the cosine function, which we know looks like this. Right, so this is basically, this is 0. I'm putting in the markings since we've compressed it by 2 pi. This is where the integers fall. The point is, this function bounces around like that. It oscillates. So the limit of cosine of 2 pi x does not exist. Now, does that mean, however, that the limit that as a sequence, the limit also doesn't exist? And the answer to that is no. If you look at what cosine, let's just evaluate a couple of terms of this, and what you'll see is that a1 is equal to the cosine of 2 pi times 1, which is cosine of 2 pi, which is 1. a2 is equal to the cosine of 2 pi times 2, which equals the cosine of 2 pi, of 4 pi, which equals 1. And a3 equals the cosine of 2 pi times 3, which equals the cosine of 6 pi, which also equals 1. In other words, what we're looking at are these points right here. And as you can see, this is clearly a constant sequence. It's just the constant sequence 1. So it's actually the case that the limit as n approaches infinity of cosine 2 pi n, where we're talking, of course, about integers n, not real numbers n, this is equal to 1, even though it looks like the equivalent real valued function has a limit that doesn't exist. What can possibly explain this? This is the difference between considering sequences and considering functions over domains of the real numbers or intervals of real numbers. When you skip all these values in the middle, you don't have the oscillation problem. Now, that doesn't work for every situation. There are certainly some situations where neither of these limits would exist. The point is, you can't conclude just because the real valued function oscillates that the sequence also oscillates. It doesn't. So if I were actually to put this in terms of the theorem, what I would say is that let's define, I'll put it in red, that's fine, because this is kind of a red sort of point. Let's let f of n equal 1. Then an is equal to f of n for all, use this for all symbol, for all n greater than or equal to 1, where n is, of course, the variable we use when we're talking about integers. So really, all these purple lines actually do pass through the constant function 1 because we're skipping everything in between the integers. So this statement is true. The reason, again, I put this in here is that many people assume that all we're doing is changing x to n, but we're not. There's a real substance to this. The statement in the theorem where we say that an has to equal f of n for all index values of n has a meaning. It means that since the index values are only the integers, we don't care whether this statement is true between the integers. We only care whether it's true at the integers. And it can make a real difference in the conclusion. Here, the obvious function to define of cosine 2 pi x turned out to be the wrong function. The more relevant function where that was equal to the sequence at the integers was just the constant function 1. That function does approach a limit, and we can write the limit as x approaches infinity of the constant function 1 equals 1. Therefore, limit as n approaches infinity of an is also equal to 1. So this is an example where you have to be careful and where the true meaning of the theorem, and where you do get a different answer. You do get a different answer as to the limit of cosine 2 pi n, where n is an integer, versus cosine 2 pi x, where x can be any real number.